degree. That affects the amount of sunlight that's received on the Earth's surface by a small amount, but that's enough to have, over time, a significant climate effect. As compared to 20,000 years ago, there was an ice sheet that covered Canada and came down and covered this region too, all the way covered New York City and Minneapolis. Those climate changes were instigated by these small perturbations to the Earth's orbit, but the mechanisms that actually maintained the temperature change were changes in the surface reflectivity so they were slow feedbacks that occurred on these long time scales. As for example, as the Earth's spin axis becomes tilted a little more, that exposes the poles to more sunlight. That will melt ice and snow at high latitudes. That makes it a little bit warmer. And as the ocean gets warmer, it gives up carbon dioxide the same way that your Coca-Cola will give up carbon dioxide if it gets warmer. So the amount of CO2 in the atmosphere changes as a function of time, as a feedback to this mechanism. But those two changes, the change of atmospheric composition and the change in the surface reflectivity, fully account for these very large climate changes. And now humans are causing carbon dioxide and methane to increase far outside the range that they've existed in millions of years. And the Earth's temperature is beginning to respond to that. That's the 0.8 of a degree Celsius warming that we see so far. But there's more in the pipeline because it takes the ocean a long time to warm up in response to the change in the atmospheric composition. And let me show you one more example. There are even larger climate changes if you look at longer time scales. This is the temperature of the ocean, of the deep ocean, over the last 65 million years, where 50 million years ago it was 13 degrees Celsius, compared with today approximately 0 degrees Celsius in the deep ocean. The fluctuations from glacial to interglacial are the ups and downs of the curve, which you can hardly see because they're so frequent on this time scale. But the changes in climate on these long time scales are due to changes, primarily to changes in atmospheric composition. 50 million years ago, there was about 1,000 parts per million of CO2 in the atmosphere, compared to 385 now. The reason on these very long time scales, the amount of carbon dioxide in the atmosphere can change because the sources of CO2, which are volcanoes, do not need to equal the sinks at any given time. The sink for atmospheric carbon dioxide is the weathering process. As the rivers carry sediments to the ocean, the chemical reactions associated with the weathering that carries this sediments to the ocean deposits carbonates on the ocean floor, and that takes CO2 out of the atmosphere. So, and that the source, the volcanic source, depends upon continental drift. So 65 million years ago, India was still south of the continents 65 million years ago were almost in the position that they are today as far as their latitude is concerned, except for India, which was still south of the equator. But it was moving north at a rapid rate of about 20 centimeters per year, which for continental drift is very fast. And it was plowing through this Indian Ocean, which had long been the depot center for the major rivers of the world. So the Indian Ocean floor was carbonate rich, and as the ocean floor is subducted underneath the moving continent, the volcanoes put CO2 into the atmosphere, and that's what caused the temperature to increase until India crashed into Asia 50 million years ago. And then the source was diminished, but the sink, the weathering associated with as India pushed up the Himalaya mountains and the Tibetan plateau, the weathering of those mountainous regions drew CO2 out of the atmosphere, and CO2 slowly declined, and the temperature of the planet went down. Well, the bottom line from this, there are two important conclusions. One is the imbalance between the volcanic source and the weathering sink is of the order of 10 to the minus 4, 1/10,000th of a part per million per year. Over a million years, that's 100 ppm of CO2, which is a very big change. But if you compare that with the human-made rate, the human change of atmospheric composition, we're now increasing CO2 2 ppm per year. So we're 10,000 times more powerful than the natural rate of change of atmospheric composition. So humans now are in charge of atmospheric composition, or we're determining it, whether we're in charge or not. The other thing is that 50 million years ago, when the temperature was 13 degrees Celsius, there was no ice on the planet. As slowly as the planet got colder, when it got to 34 million years ago, then suddenly Antarctica began to freeze over 34 million years ago. Well, the amount of CO2, the CO2 had to decrease to about 450 parts per million in order for ice to begin to form on Antarctica. And if we put back in the atmosphere, if we burn all the fossil fuels, put all the coal and oil, the CO2, into the atmosphere, we will be sending the planet back to the ice-free state. It will take a while to get there. The ice sheets don't melt instantly. But that's what we would be doing. We cannot burn all the fossil fuels without creating a very different planet. And we've set up all of our infrastructure as if the shorelines were where they are now. If you melt all the ice, sea level would go up 250 feet. So we can't do that without producing a different planet. And everyone has agreed, all the countries have agreed, that we should avoid dangerous human-made interference with climate. But what does that mean? I think the two most important criteria should be those things which are irreversible. If we drive species to extinction, that on any time scale we can think about is irreversible. There have been global warmings in the Earth's history of several degrees Celsius, and in each case it drove more than half the species on the planet to extinction. And over tens and hundreds of thousands of years, new species evolved. But on any time scale that we can imagine, or our descendants could imagine, it would be a much more desolate planet. And likewise, sea level, it requires thousands of years for ice sheets to build up from snowfall. So if we cause the ice sheets to become unstable, that's an irreversible change. We are beginning to have effects. Already the Arctic sea ice, it fluctuates from year to year depending upon the weather. But we began to make satellite measurements in the late 1970s, and the sea ice in the Arctic at the end of the summer has been declining in general, and then the last 2 years it has decreased to a level which is only a bit more than half of what it was 30 years ago. And we're probably going to lose all of that sea ice in the summer over the next few decades because there's more warming in the pipeline, even if we stopped at 385 ppm. If we wanted to retain sea ice in the Arctic, we will need to reduce CO2 to something like 325 to 350 ppm. The ice sheet, the stability of the ice sheets, this is, the red area is the portion of Greenland that has melt during the summer. And that fluctuates. The graph shows the area with melt as a function of time, beginning with satellite measurements in the late 1970s. And depending upon the weather, it fluctuates from year to year. But there's been, in general, an increase in the area with melting. And 2007 had twice as large an area as 30 years ago.